Hello and welcome to part 3 of the lesson on internal resistance. I'm assuming you've seen and understood part 2 when we started doing calculations. We're going to continue doing that in part 3. If you get a pen, paper, calculator, you'll find it very useful to try the problems we're going to go through yourself. You can stop the video and try the problems at the suitable points. First problem, a pretty simple one. Here we have a battery, that's 4 cells connected together. We've lumped the internal resistance into a single one, and the battery is connected to an external resistance. So let's read through the question. A 5 ohm resistor is connected to a battery with an EMF of 6 volts and an internal resistance of 0.4 ohms. What you've got to find is the current in the circuit and the terminal PD. That's the voltage between the terminals of the battery. If you pause the video, you could have a go yourself. We'll go through it in a moment. Okay, this is a pretty simple problem. At the end of part 2, we demonstrated this formula. The current in the circuit is EMF over total resistance. We can use that here. The EMF is 6 volts. The total resistance, little r, 0.4, big R is 5. In series, it's 5.4 ohms. 6 over 5.4 is 1.1 recurring. But we don't like giving recurring decimals as answers in physics. It implies we know the answer infinitely accurately, which we don't, because the data were provided in the question isn't given to an infinite number of decimal places. Therefore, we round that, and 1.1 amps would be a suitable answer. What's the terminal PD? Well, one way to do it would be to work out the lost volts, current times internal resistance, subtract that from the EMF, 6. But there's a quicker way. Note that the terminal PD, the voltage across battery, is the same voltage as the voltage across the resistor. So we know the current through the resistor, we know the resistance value, we can work out the voltage across the resistor, which is the same as the terminal PD. The voltage across resistor is just I times big R. So the terminal PD is I times big R. I'll use 1.11 for the current. I don't want to introduce rounding errors in the middle of a calculation, so I'm not using my rounded value. I'll use 1.11. Multiply that by the resistance, big R, 5. The answer is 5.55 volts. Rounded 5.6 volts to 2 decimal places. Sorry, to 2 significant figures. Let's try another one. This is more like an exam question. Here we've got a circuit with a switch at the top, and the switch S is open. Resistor 5 ohms. And we're told when the switch is open, the voltmeter reading, the terminal PD, is 2.0 volts. But when the switch is closed, the voltmeter reading drops to 1.5 volts. And you've got to find the EMF and the internal resistance of the cell. If you want to pause to try that, you can pause now. Okay, the first part, the EMF, is easy. The EMF is 2.0 volts. That's what the voltmeter reads with the switch open. 2.0 volts. When there's no current going through the cell, there are no lost volts, and the EMF is equal to the terminal PD. That's why it's 2.0 volts, same as the voltmeter reading. However, the next part of the question is a bit harder. We close the switch. We have to find a way of working out the internal resistance. The first step is to find the current in the circuit. So with the switch closed, the voltage drops to 1.5 volts, and that's the same voltage as the voltage across the 5 ohm resistor. So we can work out the current through the 5 ohm resistor. I is V over R, 1.5 volts over 5 ohms. It's 0.3 amps. So we know the current. We also know the lost volts. The EMF is 2, and the potential difference between the terminals dropped to 1.5 when the switch was closed. So the lost volts is 2 minus 1.5. It's 0.5 volts. But that lost volts equals the current times the internal resistance. So 0.5 volts is a current of 0.3 times little r. Rearrange that. R to 2 decimal to 2 significant figures works out as 1.7 ohms. A final problem. Let's suppose we buy a cheap voltmeter on eBay. Well, it doesn't have to be eBay, so apologies to eBay there, no implication. But we've got a cheap old-fashioned voltmeter, and its resistance is quite low. It's only 5 kiloohms, 5,000 ohms. And the old-fashioned voltmeters, which used a moving coil and had a pointer that moved across a scale, they used to have quite low resistances. A modern voltmeter has a resistance of millions of ohms, maybe 10 megohms, 20 megohms or more. This is an old one. It's got a low resistance. And we use it to measure the terminal PD of a cell, which has an internal resistance of 500 ohms. The reading on the voltmeter is 1.23 volts. And the problem is, what is the cell's actual EMF? If you want to have a pause, you can see if you can do this yourself. Let's go through it. The first thing to note is that the voltmeter will just act as a resistor, and there will be current flowing around the circuit. And just like any resistor in the circuit, the same current that goes through the voltmeter will also pass through the internal resistor. If you're using a modern voltmeter, we usually assume the resistance of the meter is so high that the current is 0, and we don't have to worry about it. But we can't do that here. Let's work out the current. The current we can work out because we know the voltage across the voltmeter and its resistance. I is V over R. The voltage across the voltmeter is 1.23 volts. The reading. The resistance is 5,000 ohms. So 1.23 over 5,000 is the current. Can we work out the lost volts? Yes, we can. Lost volts is current times internal resistance. 1.23 over 5,000 is the current multiplied by the internal resistance, which was 500. And you'll note 500 cancels top and bottom, leaving 10 on the bottom. The voltage, the lost volts, is 0.123 volts. To get the EMF, we simply note that the EMF is the sum of the voltages in the circuit, Kirchhoff's second law. It's the voltage across the meter plus the voltage across the internal resistance. 0.123 plus 1.23 is 1.35 volts. We've just added the lost volts value back onto the voltage for the terminal PD. That's it. I hope that makes sense. If you want to find out how to measure internal resistance, watch part 4. In fact, we usually measure internal resistance and EMF at the same time, and that's what will be covered